From the moment our ancient ancestors began to walk upright, our gaze has been directed towards the heavens. And while admiring the beauty of the night sky, our ancient ancestors began to notice patterns in the stars, objects that would move against an otherwise fixed background. These wanderers, or planetos, would spark a curiosity in human beings which would evolve into the practice of astronomy. And it would be to that end, the explanation and understanding of the motion of these celestial bodies, that would drive humans to embrace mathematics. And so, in a quest to understand the truth about Earth's place in the cosmos, human beings have developed some fascinating ideas about the way the universe works. And it seems that mathematical arguments have been the reason that people began embracing the idea of truth in the first place. So now, let me tell you a short story about how a few human beings use scientific observations and mathematical inquiry to unravel the mysteries of motion, which have laid the foundations for the modern world we live in today, and how that human quest continues to captivate generations to look up and ask, why? For centuries, a large part of the world accepted the Ptolemaic geocentric Earth-centered model of the universe to explain the motion of the moving bodies in the sky. But as mathematics evolved, so too did using logical arguments to explain the natural world. And a man by the name of Nicholas Copernicus would shake things up by removing the Earth from the center and replacing it with the sun. This new heliocentric model of the universe would catch the attention of some of the greatest scientific minds of the day. It would also catch the attention of another powerful entity of human civilization at the time, the Catholic Church. And it would be the support of his ideas that would have the likes of one of the greatest thinkers of all time, Galileo Galilei, to be persecuted for heresy and condemned to a life of house arrest for embracing rational thought over doctrine. Galileo Galilei, born 1564, died 1642. He was an Italian astronomer and polymath, and has been called the father of observational astronomy. He studied falling bodies, and improved telescopes for scientific observations, of which his include the observation of Saturn's rings, lunar craters, and sunspots. And while the Catholic Church responded to Galileo's published work with persecution for heresy, even after Galileo retracted his statements as facts, his efforts did not go unnoticed. And it would inspire another great mind to pick up where he left off. Galileo was also the first to observe that the Milky Way was not a nebula, but a densely packed cluster of stars. A scientific revolution is stirring. As more and more people began taking accurate measurements of planetary orbits, usually considered circles, a few people began to wonder if the data they were collecting would fit much better if the orbits were not perfect circles, instead flattened circles known as an ellipse. Johannes Kepler was one such individual. Born in 1571 to 1630, he was a German astronomer who published A New Astronomy. And in 1609, using the astronomical observations of Tycho Brahe, who improved upon the Copernican model by abandoning circles as the paths followed by planets around the Sun. Kepler would discover his three famous laws of planetary motion. And in particular, it was his small obsession with calculating the orbit of Mars that captivated his attention to these orbital paths and their properties. In particular, Kepler's third law of motion says that the square of the period of the planet's orbit is proportional to the cube of its mean distance from the Sun. And with Brahe's data, he was able to calculate the orbit of Mars by using this property. You see, by adopting the Copernican model and applying his calculations, he found that with Mars having a period of 687 days, or 1.88 Earth years, his formula told him that Mars would have an approximate orbital distance of 1.52 astronomical units, or 1.52 times the distance from the Sun, which fits the data very nicely. So through the works of Nicholas Copernicus, Galileo Galilei, and Johannes Kepler, the stage was set for the replacement of spiritualism with rationalism as a mechanism for explaining the universe. A method that would reign supreme for its predictive power, which is only strengthened more by its accurate measurement methods. Now, at the same time, many mathematical developments began to unfold. New tools being developed by mathematicians René Descartes and Pierre de Fermat. This would pave the way for calculus later on, but until then, geometry reigns supreme. Geometry rules the world. And so we are brought to the question, what is an ellipse? The circle is the set of all points equidistant from a center focal point F, and it is a constant distance from the center, which we call the radius. In contrast, an ellipse can be thought of as a circle whose focal center has been split into two foci, such that the distance that those foci are apart is directly proportional to the length of the elongation direction along what is called the major axis of the ellipse. And this elongation of the circle is known as the eccentricity of the ellipse, and is the ratio c over a in our diagram here. Now, by definition, an ellipse is the locus of points whose sum of the distances to each foci from any point on the ellipse is constant, and that is expressed by d1 plus d2 equals a constant. Now here we can use some geometric symmetry to find that constant, and also by utilizing the Pythagorean theorem and properties of an isosceles triangle, we will find that the distance d1 plus d2 always works out to be 2a, the length of the major axis. Let's explore the ellipse on the newly created coordinate axis. By using the newly developed coordinate or analytic geometry by the likes of René Descartes and Pierre de Fermat, we can calculate distances to any of the points on the ellipse using the distance formula. And so here we can describe distances along the major axis of the ellipse, and the value c, the distance from the center to a focal point, measured compared to the distance from the center to a vertex, the outer point along the major axis, is the ratio known as the eccentricity. And here we will show using the distance formula for coordinate geometry. In fact, coordinate geometry marries geometry to algebra. So using the coordinate geometry distance formula, we can come up with an equation for this ellipse. Using the properties of isosceles triangles, we get the constant distance to be 2a. The distance formula d is equal to the square root of x2 minus x1 squared plus y2 minus y1 squared. The coordinate plane, or Cartesian plane, named after René Descartes, allows us to express distances d1 and d2 by their endpoint coordinates, one of which is p, which is xy, and the other is the coordinate of a focal point. Here we'll use c, 0 for f2 and negative c, 0 as f1. Now, applying a little bit of algebraic manipulation to the distances when plugged into the distance formula, we will get that the distance, by setting it equal to 2a, will allow us to express the formula for the equation of ellipse in terms of x and y. Now, as we simplify this equation, eliminating the radicals from the equation, expanding things out, collecting like terms, and simplifying, we can get an expression for the ellipse. And one of the things that we can also employ here is the formula that a squared minus c squared is equal to b squared by the Pythagorean theorem. So finalizing here, we can simplify the formula for the ellipse as x squared over a squared plus y squared over b squared equals 1, where a is the distance from the center to the vertex along the major axis, and b is the distance from the center to the top vertice along the minor axis. And one can adjust this formula for a shifted center. So now that we have an equation of an ellipse, and we know that the eccentricity is the ratio c over a, which, by the way, since that distance is constant, one can use two tacks and a string to trace out an ellipse geometrically. The eccentricity is going to always be between 0 and 1 for every ellipse. Kepler's 3 laws of planetary motion. Number 1, the orbits of planets are elliptical. Second law of planetary motion is that equal areas swept out are going to happen in equal time. And the third is that the period of motion or orbit around the Sun, t, the square of that is proportional to a cubed, which is the distance of the semi-major axis, or the distance from the center to a vertex along the major axis. So these are the major components of the elliptical orbits, and you can notice that the Sun is at the center of one of our focal points in our new model of an elliptical orbit of a planet moving around the Sun. Now, employing the coordinate plane, or the Cartesian plane, created by René Descartes, who lived from 1596 to 1650 and made other major contributions to the theory of equations and algebra, paved the way for Isaac Newton and Gottfried Leibniz to fundamentally transform the way we think about math. But all the credit has to go to Pierre de Fermat, who, although did not publish his results on the Cartesian or coordinate plane, also made major contributions to it in 2 and 3 dimensions. Making use of these tools, Newton and Leibniz would go to create calculus, and calculus would lead, Newton to the theory of gravitation. But it would be Leibniz's notation in calculus that we would use in modern notation today. Using the tools of calculus, we will now try to find the circumference of the ellipse, which would be an important detail to finding the length of a path of an orbit. So solving the ellipse equation for y equal to b over a times the square root of a squared minus x squared, we note that the ellipse is symmetric about the x and y axis, so only finding the arc length of a quarter of this and then multiplying it by 4 will allow us to find the complete circumference all the way around the ellipse. So applying the arc length formula here, we get 4 times an integral from 0 to some value a, and inputting our value that we solved for y in terms of x into the formula for y prime, and then using some polar substitution by letting x equal a sine of theta, we can then have the limits of integration go from 0 to pi over 2, so we get this integral here 4 times the integral from 0 to pi over 2 of the square root of a squared cosine squared plus b squared sine squared d theta. Using trigonometric substitutions often simplifies integrals of these type. However, finding the value of integrals of these type is a completely different question. And letting the eccentricity e again being c over a, or e squared being equal to a squared minus b squared over a squared, we can rewrite this circumference integral as 4a times the integral from 0 to pi over 2 of the square root of 1 minus e squared sine squared d theta. And this is the first example of what we're going to know as an elliptic integral. But because there are no antiderivatives that exist for these elliptic integrals, numerical approximation techniques are usually required to evaluate them, typically by way of infinite power series. A contributing character to our case who is worth mentioning here is Bonaventura Cavalieri, known for his principles of the connections between base areas and volumes of three-dimensional solids. As a student of Galileo, he furthered Kepler's ideas in regards to solving the problem of finding the areas under the curve, specifically of the ellipse. He would compare the area of a circle to the area of an ellipse, and use geometric arguments to reason out what the ratio of the areas must be. His thought was to envision an infinite number of vertical lines intersecting the circle and its embedded ellipse, and conclude with infinite series that the area of the ellipse would be pi times ab through a series of adding up the intersections and using the fact that the ratio of these lengths was b over a. So using Cavalieri's principle and the arguments here, this provided a precursor to the idea of a definite integral using little areas of rectangles to sum up the area under a curve using a Riemann sum. The evidence is stacking up. A natural investigation into the trigonometry of the ellipse stems again from an understanding of the circular trigonometric functions. To start, given a circle of radius r, we can embed a right triangle inside of it and use that right triangle to generate the trigonometric ratios for our circular functions. And from them, we get polar coordinates, as well as a differential equation that these relations satisfy. So when we move to the ellipse, we will have to take into account more ratios, due to the eccentricity playing a factor in its shape. And for the ellipse, the radius is no longer a fixed distance metric. Now, using the right triangle created by one of the foci of the ellipse, we can generate the equation c squared equals a squared minus b squared. And we also have e squared equal to a squared minus b squared over a squared can be rewritten as 1 minus b over a quantity squared. So we see that ratio of b over a is again playing a role here. The trigonometry of the ellipse starts with the equation of the ellipse and its eccentricity, which is sometimes referred to with the value k. And the eccentricity is going to play a role in the equations for our elliptic functions. Using what's called the normalized or unit ellipse, where the b value is equal to 1, we get the three functions, the three ratios, sometimes pronounced soon, kun, and dun. And these are functions of two parameters, u and k, where k is the, well, it's called the modulus sometimes, but it's the eccentricity of the ellipse. And so these are our elliptic functions. They are functions of these parameters. And if we let k equal to 0, these will give us the circle. The study of elliptic functions plays a central role in number theory and modern cryptography today. So next, if we were to let k equal 0, that is, if we were to have no eccentricity, then we'd be talking about a circle, where a is equal to b, which is equal to r, the fixed distance. And the trigonometric elliptic functions would degenerate to our sine, cosine, and the last one just to the value 1. However, now since there are some new eccentric personalities here to have a conversation with, we will get a few new relations similar to the trigonometric Pythagorean identities. Notably here, we get kun squared plus sun squared equals 1. But because of the eccentricity, we'll generate a second equation here, a second identity. And using x squared plus y squared equals r squared and relating that to the third elliptic function, dun, we can rewrite this equation, x squared plus y squared equals r squared, in the following way. We get dun squared plus k squared sun squared equals 1. So now we have two elliptic trigonometric identities. These identities will help us generate derivatives for these elliptic functions. Pause the video now to see if you'd like to try to derive the derivatives. So here are the derivatives for sun, kun, and dun, and here are their graphed functions. It follows from these that the elliptic functions satisfy nonlinear differential equations much like the circular ones do, and therefore they have applications in partial differential equation solving. The differential equation here is satisfied by our elliptic functions, taking on the general form given here. Elliptic functions are just as useful in solving differential equations as our friends, the circular functions sine and cosine, are. Many connections between elliptic functions and elliptic integrals have been made, and one of the contributors here is one of my favorite mathematicians, Leonhard Euler. Euler noticed that elliptic integrals satisfy some addition theorems with respects to the limits of integration. And since they obeyed these addition theorems, later you see that they actually have a correlation to the angle sum formulas we see in trigonometry. Leonhard Euler made many contributions to mathematics, including in the area of elliptic integrals. The addition theorems turn out to be exactly what we think in terms of the sum angle formulas for sine, cosine, and tangent in terms of the elliptic functions. And again, if we let k go to 0, we get the natural formulas for the sum angle formulas for sine, cosine, and tangent. So this is a nice little connection between these new transcendental functions and the circular functions we are familiar with. Further results on elliptic integrals was made by the French mathematician by the name of Adrien Marie Legendre, who lived from 1752 to 1833. Legendre classified elliptic integrals into 3 kinds. Noting that the integrands take on a particular form involving a rational expression, involving a square root of a polynomial of degree 3 or 4 with no repeating roots. Later work by the mathematician Karl Weierstrass would pave the way for more number-theoretic applications to elliptic integrals and elliptic functions. Legendre also made contributions to physics as well as to his Legendre polynomials. Further progress was made by the mathematician Carl Jacobi, sometimes called Jacobi, lived from 1804 to 1851. You might know the name from the Jacobian determinant. But Jacobi made notable contributions to understanding these transcendental elliptic functions. By exploring these eccentric personalities on the complex plane, he really seemed to perk up the study of elliptic functions by discovering theta functions, involving a component called a gnome, which shows the relationship to elliptic integrals, and that they are elliptic analogs to exponential functions, and they can be used to express these elliptic functions. Theta functions are used in the study of what's called a modular form. Modular forms are complex analytic functions on the upper half plane, which satisfy a functional equation as well as a growth condition on modular groups.